When the writing starts deteriorating, just shout again. Okay, all right. Okay, so this last lecture, well, the title says it. I want to talk almost exclusively about VN periodic stuff using what I did in the previous two lectures. So first of all, for the whole lecture, there's a fixed prime p, and everything is going to be implicitly p localized because I don't want to drag along in the notation a p. Okay, so to motivate sort of the definition or the construction of VN periodic unstable homotopy theory, let me just do a very quick review of localizations in stable homotopy theory. So this is very closely related to what Natalia was talking about, or some of the things she's been talking about. So localizations in stable homotopy theory, how does that work? Well, there are many, but I want to single out a very particular class. So let me start at the very bottom again at the simplest localization, namely rationalization, right? So one way to think about rationalization, so I'm going to say something fairly tautological, but it's really the same as killing all torsion, killing all p torsion, right? So killing all p torsion, or all p power torsion. So one way to say this is there's a cofiber sequence or you could say there's a Verger quotient, but well, here it's really just a cofiber sequence of stable infinity categories as follows. So you could think of rational spectra as whatever you get from spectra by really quotienting out, in the sense of stable infinity categories and exact functors, just quotienting out all the torsion spectra, okay? So these are the torsion spectra. Where's the normal eraser thingy? Oh, here. Okay, so one thing to note about this localization is that it's, well, it has many nice properties, but the one I want to single out is the fact that it's in some sense finitely generated. So the kernel is generated under colimits by finite objects, okay? So note, this localization is, let me just put this in quotation marks, finite. I'm sure there is some technical term, but I don't think I actually know it. In the sense that the kernel, so that's this category of torsion spectra, is generated under colimits by finite objects, right? So finite spectra. So in general, you know, there are many possible localizations of the category of spectra, but there are not that many that have this particular property. The great thing in particular is these can be completely classified, these finite localizations, and that's exactly what this thick subcategory theorem that we've already seen several times is doing. Because generally, what you can do is whenever you look at these kinds of what I'm calling finite localizations, well, such a thing is precisely specified by, well, saying what the kernel is. So you could take the kernel of such a thing, such a localization, and that gives you, at least if you look at the finite part of the kernel, it gives you a thick subcategory. Of the category of finite spectra, and this is a one-to-one correspondence, okay? So it's, all right. And well, as we've seen these thick subcategories of finite spectra, these have been classified completely by Hopkins and Smith, right? So let me just repeat it once more. I think it's already been on the board twice, but well, It's a good theorem, so it doesn't hurt to state it again. So the thick subcategory theorem, it just says that every non-zero thick subcategory is of a very particular form. In particular, they form a nested sequence. So every non-zero thick subcategory of finite spectra is, is one of the following sequence. So I'm going to label them pretty much the same way that Natalia did. So spectra greater than or equal to 0, greater than or equal to 1, etc. Where this very first one is just, oh, I should put fin everywhere, sorry. So it starts with the entire category of finite spectra. That's of course a thick subcategory, and then there's a nested sequence of thick subcategories contained in that one. And one way to describe them is to say that this is precisely those finite spectra, such that if you evaluate the Morava K theories on them, then this is 0 for m less than n. Okay, so these Morava K theories are a tool that allow you to sort of detect these particular thick subcategories. Okay, so maybe, well, if you don't know what the Morava K theories are, that's okay. Let me just give examples of the first 2 or 3. And those are sort of already enough to keep in mind. So the very first one, so this spectra at least 1, this is precisely the subcategory of torsion spectra. Finite torsion spectra. Okay, so the 0th Morava K theory is precisely rational homology. So this category is those things for which the rational homology vanishes, so that's the torsion spectra. Okay. The next guy turns out to be, well, you can also describe it in terms of topological K theory. This is precisely those X such that the Ku homology of X is 0. And then for the higher ones, well, you need to use fancier cohomology theories. Like you could, yeah, anyway. I'll just leave it like this. By the way, the condition here, you can actually phrase it a bit sharper. You could have said only Kn minus 1x is 0. It turns out that implies that all the lower Morava K theories are 0 as well. All right. Okay, so let me introduce a bit of terminology. So I'm going to say that a spectrum is of type n precisely if it's in this nth category but not in the next one. Okay, so a finite spectrum V is of type n if V, if it lies in this category, so in particular all of the Morava K theories up to n minus 1 are 0 on V, but it's not in the next one. Okay, so that's the condition that the nth Morava K theory on V should not vanish. Okay. All right. Again, I'm forgetting the fins, but that's what I'm getting to. I also want to sort of use the same notation for all of spectra. So I'm going to write this, so spectra at least n for the subcategory that is, well, of all spectra that's generated under colimits by these guys. Okay, so it's the localizing subcategory generated by the type n spectra, if you will. So this is generated under colimits by this. Okay, so it's whatever's generated by the type n spectra. So one word of warning, of course, you can't necessarily give the same description. So you could try to delete the fin here. That's not necessarily a description of this category because you run into issues with the telescope conjecture and some other things. Yeah. Anyway, so that's that's the notation that I want to use for this talk. So these subcategories of type at least n spectra, they give well a stratification of the stable homotopy category. That's it's completely intrinsic. I mean, it's completely intrinsic to the structure of the stable homotopy category. And well, as with any stratification, there's there are two things you want to do, or filtration you might call it in this case. It's you want to understand sort of the associated graded here. You want to understand the individual pieces, and then you'd like to understand how to piece them together. And that's really what the subject of chromatic homotopy theory is all about. Like, you understand the layers of the filtration, hopefully, and then you try to assemble. So let me make the following definition, and this is sort of an abstract definition that I'll make a bit more concrete. So maybe the terminology I'll use is a bit non-standard, but it fits this talk. So let me define the infinity category of Vn periodic spectra to be, precisely sort of the nth graded piece in this filtration. So I'll write this for, you take spectra of type at least n, and then you mod out this. So by modding out, I mean the same as over there. You take the cofiber, you take the Verger quotient. So this, I'm writing it in a sort of non-standard way. I'm writing Vn periodic spectra. This is really just the same thing as what's more commonly denoted as Tn local spectra. So I might also just use that notation. But this is one way to introduce this thing. So it's just the associated gradient of this, this chromatic filtration. Yeah? Sure. Is there a particular one that's not readable? You just read them, yeah. Is it these ones, the n and this? Yeah, okay. All right. Yeah. Sure. Yeah, yeah. Yeah, I mean, you could say it's it's the smallest stable thing that it contains this guy, and it's closed under direct sums. And then, you want to close up under cofiber sequences in 2 out of 3 and blah blah blah. And then, yeah. I mean, yeah. I mean, you don't need to talk at the level of infinity categories or model categories anyway, right? All of this you could have said it on the homotopy category essentially. So, yeah. Okay. Other questions? All right. So let me make the description of this category a bit more concrete, and to do that, let me introduce the notion of a Vn self-map. Right. So what's a Vn self-map? So these will only exist on type n spectra. On a type n finite spectrum V. So this is a map. Well, it's a self-map. So this is a map of the following kind. So it goes from V to itself, but you can allow yourself some shifts. It's a map little v from some suspension of V to itself such that the following holds. If you look at the effect in Morava K theory of this map, then this is, for m is equal to n, it's an isomorphism. And for all m different from n, it's nilpotent. Okay. All right. So these play a very important role in the theory. Maybe just 2 quick examples. So for n is 0, this is quite simple. Multiplication by p is always a V0 self-map. Right, so in this case, the requirement is that you're an isomorphism in rational homology. Well, multiplication by p certainly is that. And it has to be nilpotent in all of the Morava K theories, but those turn out to be of characteristic p. So multiplying by p is going to be 0 pretty quickly. For n is 1, this is this famous Adams map that we talked about on Monday. So the Adams map on the mod p Moore spectrum, let's say. That's an example of a V1 self-map. Okay. So one thing that's not at all obvious from the definition is that these things exist, but that's another big result of Hopkins-Smith. You know, these things always exist, and well, they're unique in a certain weak sense. So let me give the statement. So any finite type n spectrum admits a Vn self-map. And, well, I was mumbling something about uniqueness. I like to use the phrase asymptotically unique. So what I mean by that is, you know, if you had two Vn self-maps on the same spectrum, then they're not necessarily the same or homotopic, but if you take high enough powers of both of them, at some point they become homotopic. Okay. Right. So, well, there are many very useful features about these Vn self-maps. Maybe one quick thing to note is that if you have a Vn self-map on a type n complex, then the cofiber of that map is always a type n+1 complex. So sort of you can, in some sense, use these things to give inductive descriptions of type n complexes. I mean, that's not how the proof of the existence of those complexes works, of course, because the logic went the other way around. But another thing is well, the thing I'm going to use this for now is it allows you to define the periodic homotopy groups. Okay, so a map of spectra is called a Vn periodic equivalence if it induces an iso, well, on the Vn periodic homotopy group. So what that means is it induces an iso on the groups. Well, I can always do the following. I can form the mapping spectrum from V into a given spectrum. I could take the homotopy groups of this. So this is like homotopy groups of something with coefficients in V, if you will. But I have this self-map on V, like this Vn self-map, that acts on this collection of groups. So I could invert it, okay? So this gives me a notion of periodic homotopy groups, so they're with coefficients in V. And I'm going to call a map of spectra Vn periodic equivalence if it induces an iso on these groups. So this looks a bit like a funny definition because it looks like I made a bunch of choices. I had to choose capital V, and I had to choose little v, but the choices are not particularly relevant because little v, I said it's essentially unique. This asymptotic uniqueness tells you that the choice here didn't matter. And actually also the choice of capital V. For this notion of Vn periodic equivalence, it doesn't matter because of the thick subcategory theorem. Okay, so this really only depends on n, and not on any of the other choices. Well, it also depends on p, but I fixed that earlier. Okay. So here's a little proposition that is actually not even, well, if you give yourself all these big theorems, this proposition is not difficult to prove, so maybe you could take it as an exercise. This sort of abstract category that I just defined, Vn periodic spectra, it is precisely the localization of spectra at these equivalences. So this is the localization of spectra at the Vn periodic. Equivalences. Okay, so one reason that this is a useful characterization from the point of view of this lecture is that this whole business of thick subcategories, that's not really something that you can directly try to lift to the unstable setting in a very useful way. Well, okay, I'm exaggerating, you can do something, but this characterization is something that you can lift much more directly to the unstable setting. So that's what I'm going to do. Right, so I'm going to switch to like Vn periodic homotopy theory for spaces. Okay, and the point is you can play much the same game. So, yes? Sure. 25 to 50% bigger. Yeah, thank you. Yeah, I will try to do that. Okay, so for spaces, I'm going to say that a pointed space is of type n precisely if its suspension spectrum is. Okay, and similarly, a Vn self-map is a map. I just copy the definition. It's a map like this, such that if I stabilize it, it is a Vn self-map. Oh, sorry, I did not say this was a finite space. Yeah, thank you. Yeah, no, I'm only interested in this definition for finite spaces. Yeah, thanks. So I can make the same definition of periodic homotopy groups. I mean, the formula I wrote makes sense for when everything's a space. And so I also get a notion of Vn periodic equivalence. And I'm going to localize the homotopy theory of pointed spaces at these equivalences, right? So this here is the localization of pointed spaces at the Vn periodic equivalences. And I already mentioned this on Monday, but it's not quite obvious that this exists if I just say it like this, but Bausfield proved that this is well behaved and you can actually do this. All right. Okay, good. So as I said, the main thing that I'd like to explain, to some extent at least, is the following theorem that this Vn periodic category, which by the logic that I was just explaining, you should think of it as a generalization of rational homotopy theory, right? Rational homotopy theory was the bottom part, the very, zeroth graded piece. And these are the higher graded pieces of homotopy theory in some sense. And, the point is that they admit similar descriptions, similar to rational homotopy theory. So I want to explain something about this result. So the infinity category Vn periodic spaces is equivalent to that of Lie algebras in the sense of yesterday's lecture. So these are spectral Lie algebras. In this, infinity category of Vn periodic spectra of or Tn local spectra, whatever you prefer. Sorry, there's no assumptions on what? No, that's also something that came up on Monday. But once you pass to this Vn periodic business, sort of the notion of connectivity kind of disappears. There's no, if you take a space and you take a highly connected cover of it, then the map from that connected cover to the space is a Vn periodic equivalence because of this sort of periodicity. Also, stably, like any spectrum that is Tn local and connective is contractible. So, there's no interesting notion of connectivity here. All right, so that's the theorem that I'd like to explain. So the very first thing I would want to explain about it is what the functor is that implements this equivalence. Because in particular, there has to be some functor. If I forget the Lie algebra structure, there should be some functor from Vn periodic spaces to Tn local spectra that is, interesting in the sense that that functor can be equipped with, its values have Lie algebra structures, and then it becomes an equivalent. So that functor is the Bausfield-Kuhn functor. So let me talk about that one for a bit. Okay. So this is really a sort of a magical functor that is, I guess, dear to my Hart, its definition is not complicated if you give yourself the periodicity theorem. Yeah. It's a map of spaces that gives an isomorphism on Vn periodic homotopy groups, defined in that way. So I fix a finite space of type n, I fix a self-map that gives me a notion of periodic homotopy groups. And a map x to y is a Vn equivalence if it gives isomorphisms on those homotopy groups. And then I claim that that definition doesn't depend on any of the choices that I made. It only depends on n. It only depends on the type of the space V. No, the groups are not, so these groups, so if V is a finite space of type n, X is a space, pointed space, these groups depend on much more than the suspension spectrum of X, right? So these are unstable homotopy groups, yeah. Okay? Other questions? All right. So, well, here's how you construct, something close to the Bausfield-Kuhn functor. So let me first construct what's called the telescopic functor associated to capital V. So the telescopic functor phi V that goes from, let's say, pointed spaces. Oh, I should keep my handwriting large. To Tn local spectra, this is defined as follows. What you do is, if you have a pointed space X, so I'm just going to write down the constituent spaces of this spectrum. So the zeroth space of this spectrum is the space of pointed maps from V to X, and then well, actually, the dth space of this spectrum is the same, and then for any multiple of d, that's still the same. Okay, so generally when I define a spectrum, I only have to define it on a cofinal subset of the natural numbers anyway, so I'm only going to use these multiples of d, and then I have to tell you what the structure maps are. So the structure maps of this spectrum look as follows. So what I have to do is, to get from this space to the next guy, I have to give you a map into the default loop space of phi Vx k plus 1 times d. So now if you look at how I define these spaces, this was pointed maps from V to X. And this here is the same as pointed maps from the default suspension of V to X. And now what I can do is I can precompose by this self-map little v. Okay, so that gives the connecting maps, and this defines the spectrum. And one feature of this spectrum, which is more or less direct from the definition, is that its homotopy groups are the V periodic homotopy groups of X. Right, so you observe the homotopy groups of this Vx, just from the construction, these are the V inverted homotopy groups of this mapping space. Right, so in other words, a map between spaces is a Vn periodic equivalence if and only if it gets sent to an equivalence by this telescopic functor. So one thing that's of course a bit awkward still is that I have this choice of V floating around, and I kind of want to get rid of it. So there's a better way to sort of package these things. There's a way to sort of package all of the different choices of capital V into one functor, and that's the functor that's called the Bausfield-Kuhn functor. Well, any finite spectrum, if you suspend it sufficiently many times, it's a suspension spectrum. That's yeah, that's how finite spectra work. Yeah. So you can always do that. And the same for maps, right? If you have a map between finite spectra, if you suspend it sufficiently many times, it's the suspension of an actual map. But finiteness is important, obviously. Okay, so the Bausfield-Kuhn functor, as I was saying, it packages all of these things into one. So this is a functor phi from pointed spaces to Tn local spectra, which has the following properties. So if you look at phi and you want to look at its homotopy group sort of with coefficients in V, so really that amounts to smashing it with the Spanier-Whitehead dual of V, right? The homotopy groups of this are the homotopy groups of the function spectrum from capital V into phi. Then this reproduces this telescopic functor that I just defined. So that's what I mean when I say it packages all of these things into one. And the other property, and this is really the sort of the reason why the Bausfield-Kuhn functor was invented or introduced in the first place, is that if you compose it with loops infinity, so loops infinity is a functor from, well, spectra to pointed spaces. I can then hit it with phi. The result will be some functor from spectra to Tn local spectra, and the claim is it's the obvious functor. So this is Tn localization. Okay, so let me maybe put an exclamation mark here. So this property looks kind of innocent, and it's not hard to prove. If you just sit down and again you give yourself the periodicity theorem, which we've done anyway to do any of this. Then these things are not hard to check. Like all of this is sort of straightforward. The insight is really in the idea that such a thing even exists, because this is really this is a magical thing somehow. It's telling you that the Tn localization of a spectrum, first of all, it depends only on the zeroth space, because so it factors, this functor factors over loops infinity. So you can just take the zeroth space. So that in itself doesn't maybe sound too surprising, because, well, I mean, the zeroth space, it remembers the connective cover of your spectrum, and we don't really care about connectivity, so okay. But this is really only as a space. I'm not remembering the infinite loop space structure. I'm not remembering that it was E infinity in any particular way. So this is saying that, you know, at least in this sense of Vn periodic homotopy theory, infinite loop spaces have unique d-loopings, which integrally isn't true at all, right? I mean, a given space might have many different infinite loop space structures, but this cannot happen in Vn periodic homotopy theory. And this sort of equation alone allows you to prove many interesting things. So for example, Dustin, I think he's on vacation, he's not around right now, and Akil, they give a proof using essentially only this, for example, Tate vanishing in the Tn local context. Just the existence of the Bausfield-Kuhn functor buys you a ton of stuff. So, yeah. Yeah. Yes, it is. It is only a pre-spectrum. This is not difficult, yeah. Yeah, I mean, I'm not going to do it now, just for time, but it's, yeah, you take that as an exercise, yeah. It's not difficult. Right, what else did I want to say about this? I had some comment to make, it just slipped. Well, it will come back, or not. Uh-huh. No. So, okay, so the question is, I only defined phi v, so what is this? Is this the generic case, v is the Tn local sphere? You can't do that because the Tn local sphere it's not a finite type n complex. So that's why that doesn't work, like the sphere is not of type n. But the thing that you do to get this functor really, well, roughly speaking, what you do is you take all these phi v's and you take the limit over all choices of v. So that doesn't really make sense because that limit seems like it's a bit too large, but you can make it smaller. The idea is correct, you have to implement it with some care. Okay, so one thing to note is that just by construction, this Bausfield-Kuhn functor that I am describing, it factors over a functor defined on Vn periodic spaces. Okay, because in particular, the Bausfield-Kuhn functor sends Vn periodic equivalences to equivalences, so it factors over this category. And I'm going to denote this by phi as well. Now, one important result by Bausfield is that this last phi that I wrote down admits a left adjoint called theta. But that only works if you're thinking about this guy. If you're thinking about the guy that starts in pointed spaces, actually it doesn't admit a left adjoint. So it's important to think about it in this way. So actually from a modern perspective, this is not very difficult to prove anymore because you can just use some representability criterion and check. But like in the time when Bousfield was doing this, he didn't have that machinery available, so he really had to sort of construct it by hand and really build it. So he had to work harder, but actually, I mean, you get something out of his construction. It's actually useful to keep the construction in mind. Okay, so just to quickly summarize what we've got, we now have a picture of categories and functors that looks more or less as follows. So we have an adjoint pair here that relates Vn periodic spaces to Vn periodic spectra, and there's another adjoint pair which is maybe like the more obvious one. You can also just stabilize like you would usually do. So let me just put a subscript Vn here to remind myself that it's the stabilization of Vn periodic spaces, and you can check, it's not very difficult, that this stabilization really is this category. So there are two adjoint pairs relating the infinity category Vn periodic spaces to something stable, and this diagram has a nice special feature, namely the horizontal composites in this diagram are the identity, right? So phi of loops infinity Vn, well, essentially as a consequence of that property 2 there, this is just the identity functor of this category of Tn local spectra. These are two right adjoints, so the same holds for the composition of the left adjoints. Like so, okay? So in particular, Tn locally, any spectrum is a suspension spectrum, which again isn't true at all integrally. Okay, so now let me just sort of outline very roughly the proof of that theorem about Vn periodic spaces and Lie algebras for you. Let me just, I just want to sort of specify the main ideas or ingredients that go into that. Okay. So there are a couple of key steps. So the first step, this was part of some joint work at some point with Rosona Eldred and Akil, Matthew, and Leonard Meyer. So the first thing to observe is that this Bousfield-Kuhn functor actually preserves sifted colimits. So preserving sifted colimits, it just means that it preserves geometric realizations, meaning colimits of shape delta op, and filtered colimits. All right. So this is actually not difficult to prove. It's just getting the idea that this might be true. But if you try to prove this, in the end, if you unravel all of the constructions and definitions, it amounts to checking that something like map star v blank preserves sifted colimits, which isn't quite true, but it preserves sifted colimits on sufficiently connected diagrams. So if V is a finite complex, if you map out of it, so you do map star v blank, and you look at diagrams of spaces that are at least the dimension of V connected, then that preserves sifted colimits. It's sort of it's an elaboration of the observation that the loops functor preserves sifted colimits of connected diagrams. Okay, anyway, so this turns out to be true, and that's very useful because one consequence of this is that you can apply sort of the Barbek-Lurie monadicity theorem. So phi is conservative, like it detects equivalences almost by definition, and well, it preserves sifted colimits, so it satisfies the requirements of that theorem. So a consequence of this fact here is that this adjoint pair theta phi is a monadic adjunction. Okay, so in other words, Vn periodic spaces is equivalent to algebras for the monad phi theta in Tn local spectra. Okay, so that's a good first step, and now you have to figure out what this monad actually is. All right. So now the second key step is closely related to what we were talking about yesterday. So it's about, well, functors associated to symmetric sequences. So yesterday we were talking about this functor that assigns to a symmetric sequence a functor from Tn local spectra to itself, or any C to itself. So it was this thing that sends a symmetric sequence to this associated functor Fa. So this was the direct sum over all n of the sort of the extended powers with respect to the coefficients of A. So the claim is, in this Tn local setting, this assignment is it works surprisingly well. So this functor is fully faithful. So this is fully faithful. And the essential image can also be characterized in a very simple way. So the essential image consists of those functors from Tn local spectra to itself that preserve sifted colimits. So it consists of functors from Tn local spectra to itself preserving sifted colimits. Okay. So when I phrase it like this looks like a rather sort of general nonsense statement, and its statement is so simple that you'd say, you know, it's probably easy to check or something. But it's sort of deceptively clean, the statement, because this is really the heart of the matter, and this is the hardest part of figuring all of this out. At least it was to me. So this uses a lot of sort of heavy hitting. So first of all, this fully faithfulness, this relies very crucially on, well, what's usually called Tate vanishing nowadays. So that's a result originally due to Kuhn, Nick Kuhn. And it uses it twice. It's sort of the first time you use it is to see that there aren't any natural transformations between homogeneous functors of different degrees. Then you have to use it again in a very clever way that Akil once explained to me to really get this. But okay, let me not get into in too much. And then characterizing this essential image, again, this uses something due to Kuhn, but something very different. This uses a theorem that says that the functor sigma infinity loops infinity in this Vn periodic context, it sort of has the simplest possible form. It looks like, yeah, it looks like the symmetric algebra, so to speak. So this looks like, evaluated on a spectrum E, let's say, this just looks like the direct sum in this Tn local category of the extended powers of E. Oh, I should use K's, I'm sorry. Okay, and again, this is a different result of Kuhn. Okay. So the point is, you know, so in particular, this result tells you that this functor is one of this form. It comes from a symmetric sequence, namely the commutative co-operad or operad. And then to prove it for a general functor that preserves sifted colimits, you kind of resolve it in a clever way by functors of this form. And you get at it that way. Okay, so a consequence of this collection of statements here is that, well, this makes it easy to sort of talk about operads in the Tn local setting. So an operad in Tn local spectra. So in operad, we defined it as an associative algebra in here, but since this is fully faithful and we know it's essential image, we might as well have said it's an associative algebra in that image, in that category. So an operad in Spectra Tn is the same thing. Sorry. I'm inhaling chalk here. Even with the very good Lars chalk, but yeah. So it's the same thing as a monad on Spectra Tn that preserves sifted colimits. All right, and well, we have one of those lying around because this monad coming from the Bausfield-Kuhn functor, I just said it's one of that shape. Okay, so in particular, phi theta must be of that form. I mean, this is a monad on Tn local spectra, and item 1 implies that it preserves sifted colimits. So this must be of the form the sum over some sequence O of k. So you take these extended powers. So it must be of this form for some operad O. Okay? So the last thing you have to do is recognize what the operad is. And that's, well, in some sense that's not very hard anymore. That's just a it uses a trick that I already mentioned in words, namely the Bausfield-Kahn resolution. So I'll just write that down quickly. So 3 is identifying the operad. So, well, you write down the resolution with respect to Q, so like loops infinity, sigma infinity, but you do it on this Vn periodic category, right? So there's this functor, and then there are 2 unit maps to the square of that, and then et cetera, et cetera, et cetera. Some cosimplicial object like this, and what you do is you just you take this and you pre-compose it with theta, and you post-compose with phi. Sorry, theta. To get the following, well, here we would get phi theta, which is the thing we're interested in. And here, well, let me write the limit over the whole cosimplicial object that I get. If I apply phi, it's going to cancel out the loops infinity, and theta cancels out the sigma infinity. So this looks like the identity. Here I'm going to cancel out like a loops infinity on the left and a sigma infinity on the right, and what's left is sigma infinity loops infinity. But I was just, I wrote that down, that functor. That's just a co-free commutative coalgebra, essentially. Let me just call that functor sim over there. And there's sim squared, and this goes on like this. And if you think about it, this limit is pretty much what we defined to be the cobar construction of the commutative operad. I'm sweeping some details under the rug here because you have to think a bit about in which category you want to compute this limit, actually. But whatever. I mean, this is what gives you the map from this thing to the cobar construction of the commutative operad, and that's what we define to be the Lie operad. So this gives you your map. You have to check that this map is actually an equivalence. That's sort of standard Goodwillie calculus tricks. There's nothing, yeah. There are no further deep ideas needed to wrap up this calculation. Okay, so that's essentially the outline of the proof. So the hard work mostly lies in part 2, I'd say. Okay, so just to summarize, so what we're now ending up with is we have a commutative diagram of categories of the following kind. So this will resemble Quillen's theorem a bit. So we have this Bausfield-Kuhn functor phi, which we can think of as landing in Lie algebras of Tn local spectra. So formulated in this way, the theorem says this is an equivalence. We could also, well, like apply sigma infinity. Like we still have this functor that will compare to commutative coalgebras. And this diagram commutes if here I put this this indecomposables functor that features in Cazul duality as I discussed it yesterday. So this commutes, and we know that the left leg is an equivalence, but this one is not an equivalence. So that's where the difference with rational homotopy theory arises, simply because this functor is not an equivalence of categories. We saw that this is only fully faithful on the subcategory of Lie algebras that are also nil complete, and that's just not all of them. Like not every Lie algebra is nil complete. So this is not an equivalence of infinity categories. So this Vn periodic setup, it has a bias towards the left. Still, that doesn't mean that the right-hand side is useless. Very far from it. It's a good way to try to compute things. So let me try to make some comments about that. All right. So what you still always get is the following. For general X, we get what's called the comparison map. So there's still always a map that goes from phi x to, let's say, the primitives of the commutative coalgebra that you get by taking the suspension spectrum of X and T and localizing it. Or if you rather work with commutative algebras, you could dualize. Like if X is sufficiently dualizable, you don't really lose any information by going to the dual ring spectrum. Like you can form a commutative algebra, augmented commutative algebra, by taking the Spanier-Whitehead dual of X, take the indecomposables of that, and then dualize that again. Okay, so this idea of considering this map, this already features in the work of Behrens-Resk. And as I was saying, you can't expect this map to always be an equivalence. It's only going to tell you about, at most, the nil completion of this Lie algebra over here. But it turns out that in practice, actually, many of the Lie algebras that you'd like to compute are nil complete. So let me just state this maybe a bit cryptically. So Max will give a talk about this on Friday, I believe. So it's sort of a crucial theorem in this business by Aron Mohold. And in the way that I'm phrasing it here, I should also put the names of Behrens and Resk on this theorem. So this map, the comparison map, for example, is an equivalence when X is a sphere. Okay, so that is, of course, one of the crucial cases that you'd like to understand. So, all right, and well, I mean, the way I've set everything up, it seems fairly abstract, but this is really something that you can use to do calculations. So, for example, the V1 periodic homotopy groups of spheres, I mean, those were already known, as calculated by Mohold mostly, but you could get them from this quite easily. Like at height 1, this is not a complicated calculation. But also Guozhen Wang, for example, did this at height 2 and computed the V2 periodic homotopy groups of S3 for, well, I think for primes at least 5, but essentially using these ideas. So this really opens up lots of calculational possibilities. Right, so I got 5 minutes. So what I want to do actually is, rather than sort of tell you more stuff that I think I know, just give you some questions. Some open questions about this that I think are worth thinking about. I mean, you guys are all students, so you're give you something to chew on. So, okay. Maybe before I get into this, I should check whether you still have questions about what I've said so far. We'll do more at the end probably, but Now would be a good time to ask. No? Yeah, Bastian? Yeah, sorry. Okay, so the question is this all n strictly bigger than 0? The way I've stated these things now, yes. Because if I mean, you can modify the statements I'm making for n is 0, but then you do have to keep track of connectivity because, yeah. So sort of qualitatively, these things are mostly still true, but I have to be careful about the precise statements. But for example, this business with the sifted colimits and everything, that will still work also in rational spectra, but that's maybe a bit less interesting, but yeah. Okay? All right. Yeah. Yeah. So it is, okay, the question is, in the rational case, the Lie bracket was the Whitehead bracket. What happens here? That's still true, but you have to think a bit about how to define the Whitehead bracket on periodic homotopy groups. But you can. So you can define a Whitehead bracket on the homotopy groups of the Bausfield-Kuhn functor. But it's like you have to think a bit about Whitehead brackets with coefficients, so to speak, and then take some co-limit somewhere. But then with that definition, it is true that the sort of the Lie bracket from this structure here agrees with the Whitehead bracket. Yeah. Like what is the building block? So, well, what you do is you define Whitehead brackets on homotopy groups with coefficients in type n spectra. So if you have a type n v and a type n w and maps to something, some space x, then you can define a new one, which is essentially a new map, a bracket, which is defined on some shift of the smash product of v and w. And then, you know, the Bausfield-Kuhn functor is defined by taking some limit over all choices of v. So you're taking the choices of, you take the limit over v and w, and then some cofinality argument tells you that, you know, you can all put it together. Yeah. Okay. So let me be brief about these questions. So the first one is, well, the obvious one suggested by this board over here. So on what class? So what class of spaces has this convergent property? So on what class? On what spaces is the comparison map and equivalence? So you know, really we only have sort of, well, I'd say anecdotal evidence. So there are plenty of examples of cases where it works, and there are plenty of examples of cases where it doesn't work, but it's all not particularly systematic. So it would be nice to have something better there. The second question, let me see, how do I phrase this efficiently, is essentially involves Hopf algebras. So let's consider the following. So you can consider the Lie, the functor that assigns to a Lie algebra, well, essentially it's universal enveloping algebra. So one way to define the universal enveloping algebra is to take the indecomposables of loops of a Lie algebra, just loops sort of internally to this category. This is a functor that lands in group objects in co-commutative algebras. Okay, so that's something that deserves to be called Hopf algebras. These are co-commutative Hopf algebras in T and local spectra. And well, okay, I could phrase the question, is this fully faithful? Well, that would be a bit disingenuous of me because I think we're almost done proving this. In some joint work with Lucas Brandner, Jeremy Hahn, and Alan Yuan, we're almost there, I think. So almost. This is fully faithful. So I believe that this is true. So that is a version of a Milnor-Moore theorem for these spectral Lie algebras. It's telling you that the universal enveloping algebra gives an embedding of this into that. So in particular, that gives you not only a Lie algebra model for V and periodic homotopy theory, but a Hopf algebra model. So it's a certain subcategory of this that you can explicitly identify. But the question that I wanted to ask is really, so what is the structure theory? So what is the structure of these Tn local Hopf algebras? Just phrase it like that. Okay, so this might, I don't know, it might sound a bit wild, but actually I think this, in some sense, this is not so out of reach. I think by now we sort of know enough about the Tn local category that there's lots of things we can say about this, but I haven't been able to completely do this yet. So Yeah, okay, maybe I'm just going to purposely leave this somewhat vague. But this category, it's bigger. Like, this functor is definitely not fully faithful. For example, this category contains things like the localized suspension spectra of Eilenberg-MacLane spaces. Like, those are typical examples of Hopf algebras that live in here and are interesting in here, but that are completely invisible to VN periodic homotopy theory. Like, the VN periodic homotopy groups of an Eilenberg-MacLane space are 0. So you wouldn't see anything like that over here, but you would see it here. So I think this category admits an interesting decomposition where, part of it is the primitively generated stuff. That's the stuff that comes from Lie algebras, and then there's sort of an orthogonal part, which looks like, for example, things coming from the suspension spectra of finite Posnikov loop spaces, things like that. All right, I could say more, but I think I shouldn't because hour is up. So let me leave it at that.